In this video, we're really going to explore molecular orbital theory. And so what we're going to do is we're going to ask ourselves, is hybridization the last stop in determining the most accurate information about atomic orbitals and how they come together to create a shape? So it turns out that valence bond theory, which really incorporates both VSEPR and hybridization, does not fully explain all of the observed trends in bonds. So in both of these theories, bonds are created by orbital overlap. And so if we think about hydrogen, we know that we predict it looks like this. Or you could draw a structure that looks like this. But the real question is, this idea of the orbital overlap says that the orbitals are still distinct per atom. And realistically, what we actually see is our two hydrogens that kind of live under a large cloud that isn't just two distinct circles overlapped. So how can we think about how these orbitals mix together or combine? So molecular orbital theory is an educated guess to solve the Schrodinger equation. So the Schrodinger equation was covered in previous videos. And what we've learned in the Schrodinger equation is that it's really complicated. So this is like an educated guess, meaning you plug in the numbers and you see if it works out. So what we're going to be able to do is to predict which conformation of the electron orientation is going to give us the lowest energy levels. So the question is, how do we come up with the molecular orbitals for a lot of these when it uses complex math? So we are going to use the linear combination of atomic orbitals, and you'll see this annotated as LCAO. So the linear combination of atomic orbitals is the way that we will determine the shapes. And so the orbitals are either going to be added together or subtracted. So what we're going to start to think about is the two orbitals in the hydrogen, so we have 1s orbitals. So what we're going to see is two different things. So I'm going to draw one on one side and one on the other. So on this, we're going to look at shapes. So if we have the two 1s and they're both in the same face, and we add them together, or if we have two orbitals and we're going to subtract them from one another. So we're going to end up with two different orientations. When you add them together, they will become lower in energy. We're going to get something that looks kind of like a giant sphere or an oval of uniform electron density. When we subtract the two things, what we actually see is a node appear, where instead of the bond, what you basically have are two, this one is a little bit on the wrong shape, so we'll just redraw that. It tends to kind of have a little shape like this, where there's definitely no electron density here, so we have a big node, and there's the absence of one in the bottom. So when we label these, we know that when two orbitals come together, they are the sigma. This is the sigma 1s, and this is going to be called the sigma star 1s, where the star means antibonding, and we'll look at that in just a second on the next slide. So if we take our two atomic orbitals for hydrogen of 1s, and these both start with one electron, if we add them together, we're going to reach a lower in energy state. And if you subtract them, it is a higher energy state. So these here in the middle are molecular orbitals. And on the outside, we have our atomic orbitals. So the two electrons from hydrogen are combined together into the sigma 1s and sigma star 1s. So they both live in the sigma 1s, which tells us that it's going to make a single bond. Now, a couple of things. I'm going to draw a lot of these molecular orbital diagrams. You will not be asked to determine which ones they are. You will be asked, how do you put electrons into a provided molecular orbital diagram? So in MO theory, we're going to encounter two unique types of orbitals. Bonding orbitals. These do not have a node. And these are going to be similar to a sigma bond. And what we will also see is they typically have positive interactions. So an antibonding orbital has a node in the center, and they do not lead to bonds. And so we can calculate the bond order. So a bond order is the way that we can calculate, using molecular orbital theory, how many bonds we expect. So if we think about the hydrogen-hydrogen diagram I drew, and our two 1s electrons, and we have this structure here, where you have these two sigma 1s electrons. So the bond order basically asks, how many electrons are in the bonding orbitals? So these are in the regular orbitals, so it would be 2, minus the electrons in antibonding, we have none, divided by 2, that gives us 1, which is the same as what we know based on VSEPR structure. So we expect a structure that looks like this for H2. So we can use the bond order to think about how this works. So we just did hydrogen on the previous slide, but let's look at helium too. And you may be thinking to yourself, helium is a noble gas, and we know that it doesn't interact. But this molecular orbital theory is going to give us insight into why that occurs. So each helium atom has a 1s electron, has a 1s orbital. They each have 2 electrons in them. When we add these together using the LCAO, we're going to get a positive interaction of a sigma 1s and a negative sigma star 1s. So now we're going to take our 4 valence electrons from both atoms, and we're going to fill them into the new orbitals. So it goes 1, 2, 3, 4. And the bond order here is 2 electrons in the bonding minus 2 in the antibonding divided by 2, which gives us 0/2. So we in fact have a no bond. So this is concurrent with what we already knew, that helium does not create a bond. So this is just an additional explanation, and bond orders tell us about how bonds function. So as we start to think about using molecular orbital theory to inform us about molecules, there are a couple of guidelines. One, we can approximate the number of MOs as the linear combination of atomic orbitals. So the number of molecular orbitals formed is equal to the number of atomic orbitals. So in all of the previous diagrams, what we saw was something that looked like this. Oops. So if we have our atomic orbitals out here on the side, we started with 2, and we got 2 molecular orbitals, where we have one that is bonding and one that is antibonding. So in molecular theory, bonding orbitals, or the sigma, or in the next part we'll talk about pi bonds, but the bonding orbitals are lower in energy than antibonding orbitals. And molecular orbitals are filled from the lowest energy to the highest energy, also utilizing Hund's rule, which basically says degenerate orbitals are filled 1 each first. So if we have 3 equivalent orbitals, each one gets an electron first before we go back. And it's important to note that a stable bond has a positive bond order. Now, we're going to see a whole different range of bond orders. We're also going to start to see some fractional bond orders. And you can rank the strength of the bond based on the bond order. So there's 2 other things we want to think about, the HOMO and the LUMO. The LUMO is the lowest unoccupied molecular orbital. So if this up here was our hydrogen molecule, In it, they both have a 1s electron. So we have 2 electrons in the sigma 1s. But the lowest unoccupied molecular orbital for H2 is the sigma star 1s. It is just the next energetic value that has no electrons in it. And the HOMO, or the highest occupied molecular orbital, is the sigma 1s. So we can look at any molecular orbital diagram and calculate this. So this asks, what is the bond order for hydrogen 2 minus? So an extra electron in hydrogen gas. So we're going to start with our atomic orbitals. So we have our 2 hydrogens and the 1s. So we're going to start by drawing our molecular orbitals. And what we see is this. And so we know that the valence electrons here is 1 plus an extra 1. So now we have 3. So we're going to just arbitrarily distinguish those. So in the sigma 1s and the sigma star 1s, we'll distribute our 3 electrons, and it looks like this. So the bond order would be 2 minus 1 divided by 2, and that gives you 1/2. So this has only a 1/2 bond. It is positive, so it is stable, but it is not as strong as what we see for hydrogen gas, which has a bond order of 1. So one of the things we want to think about is what happens when we start to move into p orbitals. So all s orbitals mixing follows the same orientation, where we see a sigma 1, a sigma s, followed by a sigma star. And we previously drew this for the 1s orbitals, but it turns out when you do this for the 2s, it's somewhat identical. So before we talk about the p orbitals, if we start with the 2 1s orbitals, and up here we would have our next, which are 2s, you're essentially going to see the exact same diagrams for both, where we see complete mixing, and they both just mix together to create. We have a sigma 1s, a sigma star 1s, sigma 2s, and a sigma star 2s. And so you can use this for any of these, and you could write an orientation to calculate this. But when we start to mix p orbitals, we're going to actually start to see something quite different because it matters the orientation. So this first group is going to look at what we would traditionally call the sigma bond. And so we know that because it says sigma 2p. When you add them together, you're going to get this structure down on the bottom, where we see a large orbital overlap followed by a node and information on the other side, as well as a anti-bonding, which gives you the sigma star 2p. So these over here are going to be our pi bonds. And they have orientation, whether they are the PZ or PY, based on where these are. Most of the time, these are going to be somewhat equivalent. So as we start to look at the order of these, it's important to note that not all diatomics in the second period follow the same trends. So when we look at the orbitals on the left, these have a different mixing of the sigma and pi bonds than the ones on the right. And so on the left, for boron, carbon, nitrogen, we see this arrangement. And the biggest difference is actually going to be right here, where we see a change in orientation depending on which of these we want to look at. And so on the next slide, we're going to be able to do this. It's important to note that you don't need to memorize this. You do need to know how to fill them. So let's look at samples. So we have the first group here. And so in this case, we see all of the molecular orbitals are here, and they all start in the 2s. So I have not shown the atomic orbitals that would give you this. So I will draw them for this, but not for any of the others, because it just gets a little busy. You can tell that it's hard to get the arrangement in such a way that we don't make it crazy. But the way that we can fill these is by looking at the valence electrons. So boron has 3 valence electrons. 3 plus 3 gives you 6. So you would just fill starting at the bottom and go 1, 2, 3, 4, 5, 6. So in this case, we can actually say, what is the bond order for B2? So it would be the total in the bonding, which is 4, minus 2 divided by 2, which gives you 1. And so you could identify the HOMO, the highest occupied, and the LUMO for B2. Because the LUMO is the lowest unoccupied, everything above that is just unoccupied. There aren't really names for those. So let's look at carbon. Carbon starts with 4 plus 4. And so what we see is 1, 2, 3, 4, 5, 6, 7, 8. So we can calculate the bond order in this case to be 6 minus 2 divided by 2, which gives me a bond order of 2. So let's look at nitrogen, where we have 5 plus 5, and that gives us 10 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then we can calculate our bond order to be 8, because we have 1, 2, 3, 4, each with 2 in the sigma, minus our single antibonding, which is 2 divided by 2, and that gives us 3. So there's a couple of things to notice. This molecular orbital theory predicts a double bond for carbon, but there are no electrons in the sigma. So any interactions are going to be a pure p interaction that does not move along the internuclear axis, where nitrogen is going to give us this arrangement, which we do know exists. So let's look at the rest of the second period diatomics. So now we're going to look at the oxygen, fluorine, and neon, and so we could also draw our atomic orbitals, and they would look like this. Whoops. So we can see they look like this. So for oxygen, which has 6 plus 6, we have 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So for oxygen, we can get a bond order. We're going to total up the bonding, which is 2, 4, 6, 8, minus 2, 4, divided by 2. That gives us a double bond, which is what we expect. So let's look at fluorine. So we have 7 plus 7, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So our bonding in this case is going to be 2, 4, 6, 8 minus 6 divided by 2, which gives us 1, consistent with what we believe based on the Vesper and hybridization structures. For neon, we have 8 plus 8, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So in this case, it would be 8 minus 8 divided by 2, which gives us 0. So all of this is very consistent with the information that we already know. So we know that neon doesn't create a bond, and we know that fluorine doesn't. But let's take a little bit closer look at oxygen here. So this predicts a structure concurrent with what we see here. This is our Lewis dot or Vesper structure. So one of the things to note is that we haven't talked about it, but diatomic oxygen is actually paramagnetic. So this is paramagnetic, which means that it has unpaired electrons. So if we look at the Vesper structure, all of the electrons are either in a lone pair or in a bond, and none of those are unpaired. And so in order to explain the observed paramagnetic behavior, we have to use molecular orbital theory. which just tells us that all of these theories give rise to good information, but none of them are complete. So let's look at another example. And so what is the bond order for an N2? So in this case, I'm going to go ahead and draw up the structure of the orbitals. So now that we have this structure, we can ask ourselves about the electrons. So in this case, I drew both the atomic orbitals on the outside, the molecular orbitals on the inside. On a graded assessment, I would give you a structure that looks like this, probably not drawn by hand. So for N2, we have 5 plus 1, so we have 11 valence electrons, and you can either distribute them among the atomic orbitals or just add those to the molecular orbitals. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the bond order is going to be the total bonding. So 2, 4, 6, 8. So we're going to have 8 minus the anti-bonding, which will be 1. Or whoops, that'll be a total of 3. 8 minus 3 divided by 2 gives you a plus 2.5. So we have a slightly less stable bond than we did for N2 itself. So what about if we start to think about heterodiatomics? Meaning, we're going to start to be able to look at something other than a diatomic. So the same rules apply. Fill the lowest energy orbitals first. Fill any degenerate orbitals following Hund's rule. So if this is NO over here, and I will go ahead and add in, I'm going to pause the video and add in all of the atomic orbitals. So now that we have all of the heterodiatomics, one of the things that we need to know, so we have all of our MO in the middle, whoops, that should be an M. So on the left, I'm going to decide that it's nitrogen, and on the right, it will be oxygen. So then we want to add the valence electrons. So we know that there are 5 for nitrogen, 6 for oxygen. So then, while there are electrons in the outer orbitals, we can just dump them all in. So we have 5 plus 6 is 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the bond order is going to be the bonding 2, 4, 6, 8 minus the anti-bonding 2, 3 minus 3 divided by 2, which is going to give us 5 halves, or plus 2.5. So it is a stable molecule. It just doesn't have a single or a double or a triple. It has something a little bit different. So we have a 2.5 bond order. And the highest occupied level is the pi 2p star. And the lowest unoccupied level is the sigma 2p star. So this is the highest occupied, and this is the lowest unoccupied molecular orbital. So if we start to think about these, you would be provided the structures like we were at the beginning of this slide. You will have the structures, and you'll just be asked to add them in and calculate something. So what else does molecular orbital theory really provide for us? It's going to think about resonance. So both hybridization and molecular theory are really essential for how we can see this information. So if we look at C6H6, and so we have a Lewis dot structure here at the top. And so here we have an SN steric number of 3. So this is trigonal planar. And it is sp2 hybridized, which tells us that there are these p orbitals that are left over. So when we think about these, there are, for each carbon, it has a single p orbital. So now there are 6 concentric p orbitals. So these 6 p orbitals can actually create this delocalized, meaning fully spread out, delocalized pi bond. And so one of the things that MO theory and hybridization really provide us with is the ability to look at a structure and say, okay, well, here's where we can see the electrons have gone. So this is what molecular theory adds in addition to the VSEPR structures and hybridization and Lewis dot structures to give us more insight into how electrons behave in molecules.